All right, let's go to this last section. It's 10.9, the divergence theorem. Okay, what is the divergence theorem? Well, you need a few definition here before we can define it. Definition. The divergence of a vector field F equal to Px, Y, Z, Qx, Y, Z, or X, Y, Z is DIVF equal, well, it's the dot product of the partial derivative vector and the vector field F. So it's partial X of P plus partial Y of Q plus partial Z of R. Okay. Divergent measure the expansion and contraction of a vector field. The expansion or contraction of a vector field. Okay. So here come another definition. A solid E is said to be a type 1 region if it lies between two surfaces. Solid. Type 1 region if it lies between two surfaces. Okay, so this is the type 1 region, and then you can see that, you know, the solid E is this, the solid E right here. Okay. Similarly, type 2 region if E is the setup X, Y, Z, so that Y, Z is in D. U, Y, Z less than or equal X less than or equal to U2, Y, Z. E is type 3 region if E is the set of X, Y, Z such that XZ is is inside D, and U1 XZ less than equal Y less than equal to U2 XZ. Any region E of type 1, type 2, or type 3 is called a simple solid region. Or 3 is called a simple solid region. It's closed and bounded. Yeah. Okay, so here comes the divergence theorem. Well, Gauss is the one who discovered this. It is also named as Gauss theorem. I mean, he has many theorems. I don't know which one is which. Very famous mathematician. Everybody knows Gauss. Hopefully, he is the one that is very famous. That when he was a small kid, you know, I don't know if your professor tell you this story, but he was in elementary school, right, in first grade or second grade. The teacher asked the student in the class to do the summing from 1 to 100. The teacher expects, you know, every student to take about 30 minutes to an hour to finish that summing. Gauss, it took him only 20 seconds to get the summing. So the teacher was very amazed how he did that. Yeah, only 20 seconds to do that summing. It's very different from the other kid. Yeah. Okay, so here comes the theorem. Pretty amazing how he was able to prove it. The proof is super complicated. Now, the theorem does a lot of explanation how gas is leaking out of a container, though. I'll put the note here. How gas is leaking out a container, or how air gets compressed when pumping air inside a tire. Or just when how the car rolling and then the air gonna get compressed. Gas is leaking is the same as the rate of fluid flow, right? Gas is a flow, so flowing through the surface, through the container. This one, if you do the calculation, is exactly the same as the cumulative expansion, the expansion of the gas inside that container. Pretty cool. Verify the divergence theorem. Using F is equal to Z, Y, X. and E is a solid ball. X squared plus Y squared plus Z squared less than or equal to 10. Okay, first we're gonna compute the flux of F through S. Double integral S F dot ds. Well, it's a solid ball, so that means S is gonna be a sphere. X squared plus Y squared plus Z squared equal 10. It's just a sphere. Okay. We know how to parameterize the sphere using a spherical coordinate. Okay, I'm gonna parameterize S here. X equal to, well, sphere upright is 4, so 4 psi phi cosine theta. Y is 4 psi phi sine theta. Z is 4 cosine phi. And then this the full sphere here, where 0 less than equal phi less than equal pi. We do the full sphere, and then theta is from 0 to 2 pi. Okay. Most of you already know this, right? Because the last time we have this formula. Next step is the, well, F, and then do the dot product. Okay, Z for cosine phi, Y for sine phi sine theta, for sine phi cosine theta, and then do the F dot this one. Okay. Dot them up carefully. Right? So it's gonna be a what do we have here? Well, actually, for the row square here, I'm just gonna replace it by 4 square, 4 square, 4 square. 16 times 4 is 64. Sine square phi cosine phi cosine theta plus 64 sine q phi sine square plus 64 sine square phi cosine theta. Oh, we can add them up. 64 plus 64 is 128. Sine square phi cosine phi cosine theta plus 64 sine to the power 3 phi sine square theta. Okay. Okay, so here we just parameterize S. And so we have this to be a double integral over the region D. 128 sine square phi cosine phi cosine theta plus 64 sine to the power 3 phi sine square theta. dx. Replace the limit in here right away. 0 to 2 pi, 0 to pi, hundred 28 sine square phi cosine phi cosine theta plus 64. Well, I can turn the sine here into a sine and 1 minus cosine square, because if I do that, then I can work out this integral. Derivative of sine is cosine, so we get rid of that cosine, and then it's going to be a sine, so it's 3 over 3, so it's going to be 128 over 3 sine 3 phi cosine theta. Okay, I'm gonna do the sub all the way later, and then okay, so u is gonna be cosine derivative of cosine negative sine, so it's gonna be a negative 64, and then when you integrate 1 you get u, so it's gonna be a cosine phi minus cosine to the power 3 phi over 3 sine square theta. Okay, 0 pi d theta. I wrote it okay. Sine pi is 0, so I'm gonna get this thing to be a this whole thing is gonna be 0, right? Oh, and then the cosine is not gonna be 0 though, minus 64. Cosine of pi is -1, right? Minus -1 to the power 3 over 3 sine square theta. Then you have to do the minus, sub in the 0. So sine 0 is going to be 0. So it's going to be 0 minus, okay, 64. Cosine of 0 is 1 minus 1 to the 3 over 3 sine square theta d theta. Sine square theta. So I'm missing a -1 somewhere. Still 4 times 7 over 3, huh? So this is going to be a also plus 64/3 sine square theta, and then plus 64 sine square theta. Okay, so minus 64/3 sine square theta. 64 plus 64 is 128 sine square theta d theta. Sine square is the 128. Is it half of 1 minus cosine square cosine 2 theta? That is what I remember. Yeah, sine 1 minus cosine 2 theta. So this would be a 64 0 2 pi 1 minus cosine 2 theta d theta. Okay, it's going to be a theta minus half of integral of cosine is sine. Okay, so 64 2 pi minus, okay, so we're going to be 0. And then minus 0 minus the 0. Okay, so what we have is the 128 pi. Step 2. Compute. Okay. The cumulative expansion, contraction of F inside E. Okay, so this one is the triple integral E divergent F dV. Well, we know divergent F, right, is the triple integral E is the partial derivative with respect to x of, well, if you look at the vector field F here, Z yx plus Z partial derivative of y with y partial derivative of Z x dV. So what we have is just a triple integral E 1 dV. Right. Well, this is just a volume of E. Yeah, this is exactly the volume of E here. Well, a volume of a sphere, right, is the, oh, you got to redo that integral. 4/3 pi r, so it's 4 to the 3. So we have a 256 pi over 3. Okay, so that means something go wrong in here. Negative 64 minus 1. Oh, let me see. Yeah, this yes, plus so negative 2 over 3, so it's gonna be 64. Yeah, 64 times 2 over 3. Sine square theta. Oh, this is the one that's negative. Okay, so plus, oh, 64 times 2 over 3 sine square theta. If you add them up, you get 256 over 3. And so let me see the number 256 over 3 here. Let's see if it works. So it's the 128 over 3. So 128 over 3. Oh, damn. 256 pi over 3. Yeah. Man,